Welcome to the chapter on crowd simulation theory. So far, we have focused on what crowd simulations can be used for and how they can support crowd management and event planning. In this chapter, we will take a closer look at how these simulations actually work. After completing this section, you will have the opportunity to put the concepts into practice. If you are interested in creating your own crowd simulations, you can continue with the first deep dive, where you will work hands-on with simulation tools and learn how to build and experiment with your own scenarios. The second deep dive focuses on a current and rapidly evolving topic in crowd simulation research, the use of large language models, or LLMs. We will explore how these models can be applied within crowd simulation, the opportunities they offer, and the challenges that come with integrating advanced AI techniques into simulation workflows. Together, these deep dives provide an opportunity to go beyond the theoretical foundations and explore both practical applications and emerging developments in the field of crowd simulation. Let's get started with the theory on crowd simulation. One way to classify crowd simulations is by looking at the level of detail used to represent people and their movements. In general, simulations can be divided into three categories: macroscopic, mesoscopic, and microscopic. At the largest scale, we have macroscopic simulations. These models focus on the overall flow of people through a system rather than individual pedestrians. In this approach, crowds are treated similarly to fluids, and movement is analyzed in terms of aggregate flows, densities, and capacities. Simulations inspired by water physics are common examples of this type of model. The next level is a mesoscopic simulation. These models occupy a middle ground between large-scale flow models and detailed individual-based simulations. Mesoscopic simulations focus on the behavior of groups, while still incorporating some aspects of individual interactions and decision-making. Because they can capture both collective dynamics and behavior influences, they are often useful for studying simulations such as evacuations and complex crowd movements. Finally, we have microscopic simulations, which provide the highest level of detail. In these models, every person is represented as an individual agent with their own characteristics, goals, and behavior. The simulation calculates how each person moves and interacts with other people and with the environment. This approach makes it possible to study detailed crowd dynamics, route choices, congestion patterns, and individual decision-making processes. Each level of simulation has its own strengths and trade-offs. Microscopic models are generally faster and suitable for large-scale flow analysis, while microscopic models provide greater detail but typically require more data and computational resources. Mesoscopic models offer a balance between those two approaches, combining aspects of both group behavior and individual interactions. In this chapter, we will focus on microscopic simulations. To understand the origins of crowd simulation, it is useful to look beyond human crowds and back to one of the earliest models of collective behavior, simulation of birds' flocks. A major milestone in this area was Reynolds' model, often referred to as the Boyd's model, developed in the 80s. Although it was originally designed to simulate the movement of birds, the underlying principles have influenced many later crowd simulation techniques. The key insight of Reynolds' model was that complex group behavior can emerge from a small number of simple rules, followed by each individual. Rather than controlling the flock as a whole, each bird makes decisions based on only its local surroundings. The model is based on three main behaviors. The first is cohesion, which means moving toward the center of nearby group members. This helps keep the flock together. The second is separation or collision avoidance. Each bird tries to maintain a minimum distance from its neighbors to avoid collisions. The third is alignment, which means adjusting speed and direction to match those of nearby birds. This creates the coordinated movements that we associate with flocking behavior. When these simple rules are combined, remarkably realistic group movements emerge. Large flocks can change direction, split apart, merge together, and navigate around obstacles without any central coordination. This idea that complex collective behavior can emerge from simple local interactions became a foundational concept in crowd simulation. Modern pedestrian models often use similar principles, where individual agents follow relatively simple behavioral rules, yet together produce realistic crowd dynamics at a much larger scale. So let's look at this simulation framework. This figure illustrates a generic framework that is commonly used in crowd simulation. Although different simulation models may vary in their implementation, many follow a similar layer structure. At the foundation of the framework is a representation of the walkable environment. This defines where people can move and provides the spatial context for all decisions and actions within the simulation. At the highest level, we have event management and action planning. This layer determines the goals that people are trying to achieve. For example, a person may want to enter an event, visit a specific stage, buy food, or leave the venue. These goals are translated into a route planning request, typically consisting of a start location and a destination. The next layer is global route planning. Based on a person's goal, the simulation determines an overall route through the environment. This route may take into account factors such as crowd densities, terrain characteristics, visibility, accessibility preferences, and broader coordination strategies. The result is a planned path that guides the person towards their destination. Below that is the route following level. Here individuals begin to traverse their planned routes. At each moment, the simulation calculates a preferred direction and speed, often referred to as preferred velocity. This represents how a person would ideally like to move if there were no obstacles or other people nearby. The next layer is local movement. In reality, people rarely follow a route perfectly. They continuously adjust their movements to avoid collisions, navigate around obstacles, and respond to the behavior of others around them. At this level, the preferred velocity is adopted to account for these local interactions and temporarily deviations from the planned route. Finally, at the lowest level, we have the animation or movement system. This component uses the calculated velocity to update the position of each individual within the simulation, moving them through the environment step by step. Together, these layers create a hierarchy of decision making. Higher levels determine where people want to go, while lower levels determine how they actually get there. By combining strategic planning with local interactions, crowd simulations can generate realistic movement patterns and complex crowd behaviors from relatively simple underlying processes. A simulator needs to know where the pedestrians can walk. Let's have a look at the representation of the walkable environment. To perform crowd simulations efficiently, we need a structured representation of the environment that computers can process quickly and accurately. As discussed in the previous chapter, information about temporary event objects is typically obtained from event floor plans. For outdoor events, we can often combine these plans with public geospatial datasets that describe the permanent environment, such as streets, buildings, and public spaces. For indoor events, the event floor plan itself is often the primary source of information. When working with machine-readable data, such as public geodata, it is often possible to determine walkable areas automatically. This is done by using semantic information contained within the dataset. For example, if an area is classified as water, a building, or another inaccessible feature, the simulation can automatically identify it as non-walkable. Similarly, areas classified as roads, squares, or footpath may be identified as walkable space. However, not all data sources are machine readable. Event floor plans are often created primarily for human interpretation and may not contain the structured information required for automatic processing. In these cases, determining which areas are walkable and which are not requires manual input and verification. Once the walkable and non-walkable areas have been identified, the environment can be stored in a format that supports efficient simulation calculations. One commonly used approach is the navigation mesh or nav mesh. A navigation mesh divides the walkable environment into a collection of non-overlapping cells that together cover all accessible space. Because the mesh provides an exact representation of the walkable area, it allows the simulation to perform efficient pathfinding calculations and accurately determine properties such as available space and crowd capacity. By converting the environment into a navigation mesh, we create a representation that both computationally efficient and geometrically accurate, forming the foundation for realistic crowd movement and route planning within the simulation. Let's now take a look at level 5 of the simulation framework, action planning. Action planning is the highest level of decision making within a crowd simulation. At this level, we are not yet concerned with how many people move through the environment. Instead, we focus on what they are trying to achieve. Every pedestrian in the simulation is assigned one or more goals. These goals represent the activities or actions that motivate their movement. For example, a visitor may want to enter the event, watch a performance, purchase food or drinks, visit the restroom, meet friends, or eventually leave the venue. Based on these objectives, the simulation generates a sequence of actions and destinations. In other words, action planning determines whether a person wants to go next and why they want to go there. The output of this level is typically a set of route planning requests, often represented as start and destination pairs. These requests are then passed to the lower level of the simulation, where routes are calculated and movement is generated. The complexity of action planning can vary greatly depending on the simulation. In simple models, pedestrians may follow a predefined schedule or fixed sequence of destinations. In more advanced models, decisions can depend on factors such as waiting times, crowd densities, personal preferences, event schedules, or interactions with other people. For example, if a food stand becomes too crowded, a visitor may decide to visit a different stand. If a stage becomes overcrowded, they may choose another activity instead. These kinds of decisions can be incorporated into the action planning process to create more realistic behavior. In essence, action planning answers a fundamental question. What does each person want to do? Once that question has been answered, the lower levels of the simulation can determine how the person moves through the environment to achieve these goals. Once we know the start and goal positions for each agent, the next step is to connect these locations and determine how pedestrians will travel between them. This is handled by levels 4 and 3 of the simulation framework. Let us take a closer look at those levels, where indicative routes are transformed into actual movement paths. At level 4, global route planning, the simulation computes a route through the environment from a pedestrian's current location to their destination. Rather than calculating every individual step, this level determines an overall corridor through which the pedestrian should travel. For example, inside a building, this corridor might consist of a sequence of hallways, rooms, and doorways connecting the start and destination. In an outdoor environment, it might consist of a series of streets, pathways, or open spaces that guide the pedestrian toward the goal. The result is an indicative route, a high-level plan that specifies where the pedestrians should go, but not exactly how they will move at every moment. In level 3, route following, here it takes the indicative route and it turns it into a path that can be traversed. The pedestrian continuously follows the planned corridor, moving from one part of the route to the next while progressing towards the destination. At this stage, the simulation calculates the pedestrian's preferred direction and speed based on the route. If there were no obstacles or other people present, the pedestrian would simply follow this preferred movement directly towards the goal. In practice, the route acts as a guide. It tells the pedestrian which hallways, streets, or open spaces to use, while the lower levels of the simulation handle the detailed adjustment needed to avoid collisions and interact with the surrounding crowd. So in summary, level 4 determines the route through the environment, while level 3 ensures that the pedestrian follows that route. Together, these levels translate the destination into a navigable path that guides movement through the simulated environment. Let's now look at level 2 of the simulation framework, local movement. At the highest levels, the simulation has already determined where a pedestrian wants to go and which route they should follow. However, real people do not move along perfect straight path. They constantly adjust their movements in response to their surroundings. The purpose of level 2 is to adopt the preferred movement generated by the route following level so that pedestrians can move safely and realistically through a dynamic environment. One of the most important tasks at this level is collision avoidance. As pedestrians move, they encounter other people, obstacles, and constantly changing crowd conditions. Rather than continuing directly towards their destination, they may temporarily slow down, speed up, change direction, or move around others to avoid collisions. To better understand these detailed movement behaviors, researchers often study pedestrian motion experimentally. A common approach is to use a motion capture setup, which allows precise measurement of how people move and interact with each other. In the example shown here, two of our formal PhD students are wearing motion capture suits. These suits contain sensors or markers that record body movements with a very high level of accuracy. By tracking their positions, orientations, and walking patterns, we can observe exactly how people adjust their movements when encountering others. Using this data, we can analyze how pedestrians avoid collisions in different situations. For example, we can measure how early people start changing direction, how much they slow down or speed up, how they react to approaching pedestrians, and how these behaviors may vary between individuals. The insights gained from these experiments are then used to improve crowd simulation models. By incorporating realistic movement patterns and avoidance behaviors, simulations can more accurately represent how people move through crowds and interact with one another in real-world environments. In this way, motion capture studies help bridge the gap between observed human behavior and the mathematical models that drive crowd simulations. The previous experiments showed that people use a variety of subtle strategies to avoid collisions. For example, pedestrians may slightly rotate their bodies when passing one another in a narrow space, or they may adjust their acceleration and walking speed to create enough room to pass comfortably. These observations highlight an important point. Perfect collision avoidance is not realistic. Human movement is far more diverse and nuanced than simple following a optimal path while never coming close to others. In the video, we can see some of the limitations of a basic collision avoidance model. For example, all pedestrians move at approximately the same speed, whereas real crowds contain significant variations. Some people walk quickly while others move way more slowly or stop frequently. We also see that pedestrians behave in a very consistent way when passing one another. There is little variation in whether people move to the left or right. In reality, these choices can depend on local customs, personal preferences, and the surrounding crowd. Another limitation here is the absence of group behavior. Real pedestrians often move as families, groups or friends, or organized parties. Group members tend to stay together, coordinate their movements, and sometimes occupy space differently from individuals. And finally, everyone in the video is continuously walking. In real crowds, people may also stop, wait, talk to others, look at interactions, check their phones, or simply remain stationary for a period of time. These differences illustrate that realistic crowd behavior involves much more than basic collision avoidance. Human movement includes a wide range of individual preferences, social interaction, and contextual influences. Recognizing these limitations formed the basis of our research. The goal was to develop models that move beyond simple avoidance behavior and incorporate a richer representation of how people actually behave in crowds. By including factors such as speed variation, social groups, standing behavior, and more realistic movement decisions, simulations can better reflect the complexity of real-world pedestrian dynamics. Another important aspect of realistic crowd simulation is the representation of social groups. People rarely travel entirely on their own. At many events, visitors arrive with friends, family members, or colleagues and tend to stay together through their visit. This social behavior has a significant impact on crowd dynamics and therefore needs to be considered in simulation models. Research has shown that even when people arrive in large groups, they often naturally split into smaller subgroups. These smaller groups typically consist of between 1 and 4 people who remain close to each other while moving through the environment. To model this behavior, we developed a finite state machine model for small social groups. Rather than treating each pedestrian as a completely independent individual, the model allows group members to coordinate their movements and behave as a group. The primary objective of the group is to stay together while moving towards its destination. Group members adjust their speed and position to maintain proximity to another, often sacrificing the most direct route in order to remain connected. However, crowded environments can sometimes force groups to separate temporarily. For example, other pedestrians, obstacles, or bottlenecks may split group members apart. When this happens, the model changes the group behavior. Instead of focusing solely on reaching the destination, separated members actively attempt to reunite with the rest of the group. Once the group has reassembled, it assumes moving as a coordinated unit towards its goal. By incorporating social groups into crowd simulations, we can better reproduce the movement patterns observed in real events. Group behavior influences walking speeds, space usage, route choice, and congestion patterns, making it an important component of realistic crowd modeling. Before concluding this chapter, it is important to discuss the limitations of crowd simulation models. First and foremost, the simulation is only a model of reality. No matter how sophisticated the model becomes, it cannot fully capture the complexity of human behavior and social interactions. People make decisions for many different reasons, and these decisions can be influenced by factors that are difficult or impossible to represent in a simulation. Despite these limitations, crowd simulations can still provide valuable insights. When a large number of pedestrians follow realistic local rules for movement, navigation, and interaction, meaningful patterns emerge at crowd level. These emergent patterns often correspond well with what we observe in real-world situations and can provide useful information from a statistical and operational perspective. For example, simulations can often predict where bottlenecks are likely to occur, how crowd dynamics may evolve, and how changes to the environment might affect pedestrian flows. These types of aggregate behaviors are generally more predictable than the actions of individual people. However, simulations are much less effective at predicting unexpected individual actions. A model may estimate how a crowd will behave on average, but it cannot reliably predict when a person will suddenly behave in an unusual way. For example, an individual may unexpectedly start shouting, running, stopping, or behaving in a manner that influences those around them. Similarly, simulations can only account for environmental conditions that have been explicitly included in the scenario. Unexpected events such as lightning, sudden weather changes, infrastructure failures, or unforeseen incidents are not automatically captured by the model unless they are incorporated into the simulation assumptions. For this reason, crowd simulations shouldn't be viewed as tools that predict exactly what will happen. Instead, they should be seen as tools for exploring possibilities, understanding trends, and evaluating the likely consequences of different assumptions and decisions. When used appropriately, simulations provide valuable support for planning and decision making. They help us understand what is likely to happen under certain conditions, while recognizing that real-world events will always contain uncertainty and unexpected behavior. To conclude this chapter, let us reflect on some important questions and discussion points related to the use of crowd simulation. The first question is how we should deal with the fact that every simulation is a human-made approximation rather than a prediction of the future. As we have discussed, simulations are built on assumptions about the environment, the people within it, and the situations being studied. They can help us understand what might happen under certain conditions, but they cannot tell us exactly what will happen. This raises the question of how much confidence we should place in simulation results and how they should be used to support decision making. A second topic concerns validation. Simulations can be compared against real-world observations, such as sensor data, pedestrian counts, travel times, or crowd density measurements. This process helps us determine whether the model behaves realistically. However, even a well-validated model cannot eliminate uncertainty, because real-world assumptions are constantly changing. This leads to an important question. How much validation is enough before a simulation can be considered reliable for practical use? Finally, there is a question of transparency and understanding. Modern crowd simulations often rely on complex algorithms that generate emergent behavior from many local interactions. The resulting crowd patterns may be realistic, even though the underlying calculations are highly technical. This raises the question of how much users need to understand about the algorithms themselves. It is sufficient to understand the assumptions and limitations of the model, or should decision makers also understand how the underlying mechanism produce the results they see? These questions do not have simple answers, but they are important to consider whenever simulations are used to support planning, risk assessment, or operational decision making. Understanding both the capabilities and these limitations of simulation is essential for using these tools responsibly and effectively.